Hello, my name is Rob Reynolds. Welcome to Business Calculus, section 3.4. Today we're going to get some word problems, optimization problems, and the strategy is to write two equations, plug in one equation for the other equation, or the substitution method, and then we're going to take the derivative, which is, of course, how to find a max or a min, or to optimize the problem. You're going to need to know some formulas here. For the real-life situations, you may need to know the perimeter and of a rectangle or even a semicircle. This is to maximize this particular figure, which has a semicircle in it as well. So you can see that's 2 pi r divided by 2. So you're going to have to know some formulas here, and we'll help you with those as you go through. So again, here's the general strategy that we're going to use for these things: writing two equations, substitution, and then the derivative. And again, this is just to optimize, to find the maximum profit, or whatever. In this case, we're going to be dealing with volume. Let's see, sometimes we're maximizing surface area, so we just have to read real carefully. So the first thing I see is, what are the dimensions of the box to maximize volume? So the volume of this box is one of the equation. And of course, it's length times width times height, but in this case, it's x times height. And then they do talk about surface area. So the surface area is the area of the front face, which looks like an x by h. And I've got 4 of those x by h's, because there's another x by h, and so on and so forth. And then the bottom of this thing is an x by x. And I don't think I have the top, so you have to read real carefully. There might only be one x squared function, and if that's true, then it's x squared plus the 4 xh's for my total surface area, which is given to be 108. So there's an equation, and this is one I want to maximize. So I got the two equations. Now I'm ready for the substitution. And in order to substitute, we need to solve for one variable and plug in the other. There's multiple ways to do this, but maybe the easiest way is to solve for this h here. So I'll say 4xh is equal to 108 minus x squared, and h is equal to 108 minus x squared over 4x's, and that is going to be plugged in right there. So let's go maximize the volume by taking the derivative, which we've learned how to do, and set it equal to 0, and then look for maxes and mins by the first derivative test. Before we do that, you may want to simplify, if at all possible. So let's rewrite the volume function. Let's see, this is going to be 27x minus 1/4 x cubed, because you still have 1x floating out here that gets distributed to make that an x cubed. And then I can find the derivative of this thing, 27 minus 3/4 x squared, set it equal to 0. I'll say 27 is equal to 3/4 x squared, just so I have positives. I'll multiply both sides by 4/3, take the square root of both sides, and end up with x equaling 6. Once I decide that x is 6, I can find the dimensions of h by plugging that back into this formula. So I'll say, remember the surface area was 108 x squared plus 4xh. So I'll just solve for this thing. Let's see, x is 36. So let's say 108, no, x is 6. So 6 squared, 36 plus 24 h's. So 72 equals 24h, and h will equal 3. So now I've got everything I need to know. I could even go back and find the maximum volume by plugging in my x and my h to find the maximum volume. So again, you're certainly welcome to see how the author worked this out. If you haven't already, go to Blackboard and print out a blank worksheet so you can work along here with me, and then there's a PDF file with worked out solutions as well. So there it is, x equals 6 and x equals h. Here are the guidelines that the author uses. Find out two equations. This is the substitution, and determine the derivative using the first derivative. Example number 3 talks about a rectangular page, and and it looks like we'll call this a y distance, and we'll call this an x distance. So then they start talking about 1 inch width. So there's 1 inch and there's 1 inch. So the 1 inch width, so there's a 1 inch and there's a 1 inch. So this total length up here is actually y plus 2 from here to here. And then they say this is 1.5 inches from the top and the bottom. So this distance from here to here, if this is 1.5 up here and 1.5 up here, this total distance is x plus 3. So again, trying to come up with a nice picture for this thing was really helpful. And we want to maximize, or excuse me, minimize. And I'm going to use this area, x plus 3 times, see, this is going to be y plus 2 for the area. And the substitution would come from this guy, 24 square inches of print. So we know 24 is the xy. That's this area inside here. So this is the x by the area is 24 is given. So if that's true, then I could substitute in my y is equal to 24 over x, and that can get plugged in right here. So x plus 3, 24 over x plus 2 is my new area formula. Let's clean that up a little bit. Foiling that out, 2x plus 30 plus 72 over x. And then I'll go ahead and take the derivative of that. So 2 minus 72 over x squared. I'll set that equal to 0 and solve. 72 over x squared is equal to 2. So if I set that equal to 0, 72 equals 2x squared, and 36, to take the square root of it, plus or minus 6 is my x. But of course, negative 6 doesn't make any sense, so I'll just say positive 6 is my x, and I'll substitute that back in, and y will also turn out to be 6. And then once I have the values for x and y's, I can answer any questions that they may ask. Again, here's worked out solutions. They foiled this just a little bit different because I just did the FOIL method from this. They went ahead and found a common denominator and rewrote. So I don't have this statement, but so their function looks just a little bit different than mine. Let's see if, yep, they end up with kind of the same conclusion. I can see this is, well, again, they worked it out a little bit differently, but they did get plus or minus 6. And this slide is just telling you about the purpose of why you're learning calculus in a business situation. And it's basically reminding you that the power of calculus can, you can just look at a problem, read a problem, and then figure out, oh, I can use some calculus to determine maxes and mins for these functions. So here comes some problems out of your book. These are also problems that will be similar to your quizzes and or your tests. So I kind of wanted to review a couple of things before we end the video. Two adjacent rectangles. So let's see, this is an x, this is an x. So I'm going to redraw this over here and just say, well, this is really 2 x's, that total distance. Here to here. This is a y, this is a y, and this is a y. So if I'm talking about perimeter or having 200 feet of fencing, I would say, well, I need all of this to be fenced in. So let's see, that's 4 x's plus 3 y's has to equal 200 feet. That's what I have. And I could actually spend the time to solve that for y. 200 minus 4x over 3. And I know that I want to maximize the area. So the area of this thing is length times width. But the length is 2x and the width is y, and I think I've got a nice y value here that I can substitute in for. So 2x times the 200 minus 4x divided by 3 is my area function, which I always like to try to simplify if possible before you dive in and take the derivative of it. I wonder if, I don't know if you'll buy that this is more simplified. I think it is. because 8/3 is just a constant, will just pop out. So this will be 8/3. The derivative of this guy is 50 minus 2x. So my critical value is 25. Now I know that that's a max by doing the first derivative test and just testing f prime 0 and f prime maybe 26. And then looking for intervals of increase and decrease. And I know we're looking for a max, so that means that this side should be increasing. You can test that, and this side should be decreasing. That's called the first derivative test. The second derivative test actually is pretty easy. I haven't talked about it, I don't think, yet. But the second derivative test says take the second derivative of this thing, and the second derivative of this is going to be negative 16/3. And if I plug in the critical value at this second derivative, it turns out to be negative, which talks about its concavity, which we're going to talk about shortly here. If it's concave down, that's going to cause a maximum. So I know that I have a max at 25. So either you could use the first derivative test or the second derivative test to determine. So that's what they did here. Since it's less than 0, you have a maximum. So we'll talk more about concavity. For number 13, a lot of figures here. In part A, they just said make sure the surface area is 150 units. Now remember, surface area is different than volume. Surface area would be, this guy would be a 3 by 11. And I think I've got a couple of those 3 by 11s, at least here and here. Well, in fact, I think I have 4 of them, because this front face would also be a 3 by 11. So here, and then the back face. And then the top and the bottom would be a 3 by 3. So you go ahead and find the surface area here by using the same, but I think we have 2 of those x squareds plus 4 xh's this time. So I think we do have a top this time and a bottom that we have to worry about for surface area. So make sure that all 3 of these figures is 150 units. Then find the volume of each solid. The calculus comes in here when you want to maximize the volume of the surface area. So if we have just a general object and we want to maximize its volume, again, I think we just talked about the surface area formula. I am not a big fan of that formula, although it probably works. I would probably stick with our 2x squared plus 4xy equals 150. Ugh, so let's see what they do for volume. Ugh. Well, at least they do say length times width times height. So again, I don't always like what the author says. I just would have said our volume is what? X squared y. So these are some general formulas, but I would get to these for volume and surface area. And then using those, I would probably do a substitution. I'd probably get rid of the y value by up here solving this guy for y. That might take a little bit of effort. I think y turns out to be 1 over 2x, 75 minus x squared. And then I would probably plug that in up here to maximize or minimize. So here's some general formulas. You can look these up on the internet as well. This is the Wisconsin formula sheet if you want to Google. If you're not real strong at geometry, I could see that you may want a cheat sheet for some of these, especially when they start talking about surface area of like spheres, although it's not even on. Oh, there it is. The sphere is 4/3 pi r cubed, and no one ever remembers the surface area of a sphere, which is 4 pi r squared. They creep up from time to time. So again, this book assumes that you know that, and it's been my experience that you don't. So there's answers for A and B. Of course, part C was where the real calculus came in. There's that y value that gets substituted in. You finally find the volume. You take the derivative of the volume, set it equal to 0, and they're still doing the second derivative test here to determine whether that really is a max or a min. This last problem is probably the most common calculus problem that you'll ever see. It's got to be on some quiz. It's got to be on some test. I mean, I just don't know of a Calc 1 teacher who doesn't use this problem for finding the volume of the largest box that can be handled. Manufacturers are doing this all the time. So what's happening here is you're cutting out these pieces and folding these edges up. So you can see that the height, if I fold this lip up, is actually x. So the height is x. And then the area of the base is, well, it's given right here. Well, actually, here's the base once you fold that lip up, and here's the base. So all four of those are bases, which is what? 6 minus 2x, and it's going to be length times, or width and height, or however, length and width probably. So this is 6 minus 2x, this is 6 minus 2x, and I'll square that. So the base dimensions are 6 minus 2x by 6 minus 2x, and then the height, after I fold these lips up, fold this lip up, fold this lip up, fold this lip up, and evidently I don't have a top on this box. So here's my volume formula, and I'll probably try to simplify that again before I find the derivative of this thing. The derivative of this will turn out to be 12 x minus 1, x minus 3. The critical values here, of course, are going to be x equals 1 and x equals 3. And I'll find out that 3, 0 and 1, 16 are possibilities, and I'm going to say, well, the max is at 1, so I'm going to choose that the volume is really 16. So take a look at, again, how the author worked this out, and make sure that you can work this out as well. Again, I'd be hard-pressed to say that this won't be on a quiz or a test. You should see this problem somewhere. All right, if you have any questions, feel free to email me. Thanks.